Ladies and gentlemen, welcome to the GOM Training Webinar, 2D and 3D Image Correlation in Materials and Components Testing today. We would like to discuss today the differences between 2D and 3D measurements, looking into a few applications, into issues that arise with 2D measurements, and giving you an outlook what comes next, what needs to be considered for DIC measurements. My name is Markus Klein and I'm sharing the webinar today with Julia Werkmann. So we will guide you through the webinar today. If there are any questions from your side, please let us know with the questions and answers in the WebEx tool. The audio is broadcasted over the internet. If you see problems with this, please let us know in the questions and answers too. There will be a recording of this webinar available later on, and we will upload this to the GOM service area and also to our YouTube channel so that you can review and share this with your colleagues too. The agenda for today, we would like to discuss a little bit what is digital image correlation, not really in too much details, looking on the characteristics of 2D and 3D measuring data and the applications for 2D and also 3D, of course. Another larger aspect here, the technical part of this webinar, will look into the limitations for 2D measurements, such as distortions of lenses which are used, changes of distances between camera and specimen, movement of specimen, specimen disorientation like tilting or, well, bulging happening, the cosine error causing from tilted specimens, and we will look into further applications in 3D where 2D measurements will definitively not be possible. Finishing with a summary and little further information then at the end of the webinar. This webinar will take approximately 45 minutes today, and we hope that you stay tuned for that time. So what is digital image correlation? So looking on this video here, you see a prepared part. So for image correlation, a pattern needs to be put on the part that deforms with the specimen under load for 2D or 3D cases. You see a facet, an area in this image, which is calculated using the gray value distributions inside this area. There are thousands placed on the images and thus followed throughout a series of images. In 2D, 2D coordinates are derived. In 3D, of course, 3D coordinates, which are then further evaluated for displacements, velocity or acceleration, as well as strain and strain rates. The basic results which are generated using image correlation is a full field measurement result containing thousands of measurement points, as you see them here in this screenshot from the GOM Correlate software. So 2D measurements do have, of course, a few requirements. Due to the nature that a 2D measurement only can capture in-plane coordinates, there is no motion allowed between specimen and camera, so only in-plane tests can be evaluated with this, and only specimens which are really plane. The camera needs to be positioned perpendicular looking on the specimen, otherwise issues might occur like tilting, distance changes, but Julia will go through with you a little bit later on with its limitations. In a 3D setup, 3D coordinates are measured and evaluated using a stereo camera setup, so therefore the specimen is allowed to move in 3D space and the coordinates will be calculated in X, Y, and Z, so distance changes are no problem, and the contour of the specimen also do not need to be really flat. For 2D evaluations, we can provide you a free software that you can try out, the GOM Correlate software package. You can import images in this. In combination with the GOM Correlate, there is a snap tool available, so an image acquisition software package that allows you to record images from a USB 3 camera. We will come back to this a little bit later on. With 3D systems, of course, a sensor setup is required using a stereo camera setup. Lighting is another issue that needs to be discussed, but we can offer you different configurations for different applications in terms of hardware as well as software. So here, basically, the Aramis professional software is then used. Leading over to the technical part, I will give speech to Julia now.
Thank you for the introduction, Markus. A typical application that uses a 2D measurement is the shear test. Shear tests serve for inspecting a small area, the so-called shear area. The specimen has to be flat and should mainly deform in one plane. Another application example is the inspection of a failure area. The specimen slightly moves to the low load. Often very small materials are analyzed in 2D. 3-point bending tests can also be analyzed in 2D. The purpose is to analyze where and why it comes to the component failure in specific areas. Here you can see the major strain. 2D image correlation can be used for high-speed tests. The material breaks after approximately 0.013 seconds. Super high-speed tests capturing 1 million images per second are also often recorded in 2D. 2D measurements are especially used for quasi-static tensile tests. Here you can see the longitudinal strain. Point-based inspections in 2D are also possible. Here we have an example from the field of biomechanics. You see the displacement of the leg prosthesis. Another example is a sled crash test. This test is also analyzed in 2D. The load is uniaxial. If you would like to see the 2D application in more detail, you can watch these 2 webinars. You can find the webinars for download in our service area or on the GOM Metrology YouTube channel. Let us now turn to the limitations in 2D. I will show you the limitations based on a tensile test. However, the limitations do not only relate to the tensile test, but also to all other 2D application examples. We will talk about the distortion of the lens now. Let's take a look at how an idle camera setup would look like. The camera creates an image of an object. With an idly set camera, you have a straight projection of the object. In reality, you additionally have a camera lens. The camera lens can lead to distortion. A distortion is a deviation from the straight projection of the object. It depends on the used lens. Lenses with a small focal length show a particularly high distortion. We are talking about a focal length which is smaller than 35 mm. Here you see the barrel distortion. It corresponds to the fisheye effect. This effect has influence on the deformation analysis, where only one camera is used. When an image section moves from the center to the border, it is compressed. When an image section moves from the border to the center, it is stretched. Here you see another picture of a barrel distortion. To prevent distortion, standardized geometries such as calibration panels are used. What are the advantages of the calibration? You use a rigid geometrical construction to compensate the lens distortion. To show this effect in practice, I carried out a tensile test. The lower part of the specimen moves to the image center, and the upper part moves to the image border. I recorded the tensile test in 2D and 3D at the same time. Ideally, both measuring data sets provide the same results. Let's look at the results. Here, you see the longitudinal strain, which was evaluated in a 2D test. The color representation of the surface component shows epsilon in y direction. That represents the longitudinal strain. For the 2D test, I used a lens with a focal length of 24 mm. This point shows a longitudinal strain of 38.7%. I recorded the same test also with the calibrated 2D measuring camera. When you compare both the results, you see that the result of the uncalibrated 2D measurement shows pseudostrain of about -3%. The pseudostrain results from the barrel distortion. Facets that move from the image center to the upper border are compressed. Here you see the evaluated 3D test, which was recorded with an RMS system. The 3D test serves as a reference. Here you see a longitudinal strain of +41%. That means you have still an offset between the calibrated 2D measuring data and the 3D measuring data. To show the effects in a loaded state in detail, I have constructed and analyzed a section in the middle of the specimen using GOM Correlate. The diagram shows the strain values relating to the section length. On the left, you see the upper part of the specimen. On the right, you see the lower part of the specimen. Here you again see that the strain values in the upper part of the specimen are lower in the 2D measurement than in the 3D measurement. The comparison results from the effect of the barrel distortion. In the 2D measurement, the lower part of the specimen shows a higher distortion, also caused by the barrel distortion. This difference is relevant for strain values of this extent, because the N value and the R value are determined in the range of high plastic strain. And we have almost 50% of longitudinal strain. In the calibrated 2D measurement, you can see an offset, as I said before, of around 0.5%. This deviation relates to a change of the distance between the specimen and the camera. The change in distance can result from the circumstances that the specimen is thinned, whereas the lower part of the specimen is rigid, the upper part thinned more. This means that even if you have a good measuring setup, the calibrated 2D measurement shows an offset. In the uncalibrated 2D measurement, you have a relative error of around 7% if you compare the values here. Let's have a look at the next limitation, change in distance between the camera and the specimen. Two-dimensional images require that the movement occurs in a calibrated plane vertically to the camera axis. This means that the camera must be positioned vertically towards the tensile specimen. Here we have a more precise model. Let's assume that the camera is positioned towards the specimen at the distance of G0. The camera creates an image of the specimen L0. What happens if the distance between the specimen and the camera is changed by delta G? In other words, what happens when the tensile specimen moves out of the calibrated plane? If the specimen does not stay in this plane, an error occurs. The camera image of the object L0 changes. This means that distance change influence the results of the 2D measurements. To calculate the pseudostrain, you can use this equation. This can be demonstrated by a calculation example. Let's assume that the distance between the camera and the specimen is 350 millimeters. The distance then is changed by 0.7 millimeters. Of course, the illustration is not true to scale. When you insert the values into the equation, the result is a pseudostrain of 0.2%. This value lies above the permitted elastic limits. The change in distance between the camera and the specimen can have several reasons. As I mentioned before, the thinning of the specimen can lead to a changed distance. Another reason could be a movement of the camera or the camera tripod. The movement of the camera tripod is shown in the next example. In this test, I considered only the external influences on the upper 2D measurement and the lower 3D measurement. To show the influences, I activated the deformation tracking at the same time. I constructed two extensometers to show the longitudinal and transverse strain in the GOM Correlate software. As long as the measuring system is not interfered, both show the same. But as you have seen, if someone pauses next to the camera tripod, you can have like a movement in the camera. That leads to a pseudostrain in the 2D measurement of about 0.1%. In 3D, you can't see this effect. This means that when you record a test with only one camera, your measuring results might be affected by erosions, particularly when you want to measure elastic values. Another example of a change in distance is shown by the following model. Let's assume that the camera was not positioned vertically towards the specimen. Due to the tensile force, a point on the specimen moves upwards. The camera, however, assumes due to its tilted position that the calibrated plane is placed in another position. Therefore, in the 2D measurement, the camera interprets a different movement of the point. The point is projected onto the specimen. This leads to an out-of-plane error. As a result, we have a higher strain in this case, as the calibrated plane moves towards us. Here is a numerical example. Let's assume that the point moves 150 millimeters upwards at the measuring distance of 350 millimeters. When the camera is tilted by 1.3 degrees, this corresponds to a delta G by 0.5 millimeters. If we insert it again in the equation, we get a pseudostrain of 1%, which is significant for plastic values. Let's have a look at a real example. We have again a simple tensile test with a longitudinal strain up to 50%. The camera is tilted upwards by a few degrees, but less than 3 degrees. This means that all points of the specimen surface do not only move upwards, but also backwards. Here you can see the longitudinal strain during the 3D measurement under load. 3D serves again as a reference. Here you see the 2D longitudinal strain. All points of the specimen move backwards due to the tilted setup. That's the reason why we have a lower longitudinal strain value here in the 2D than in the 3D measurement. In order to analyze the effects of the tilted setup more accurately, I inspected a section in the loaded state. On the left, you see the upper part of the specimen. On the right, you see the lower part of the specimen. At the bottom, the specimen is clamped firmly. That's why this area shows a lower strain deviation. Here we have a higher strain deviation. This effect of pseudostrain does not only occur with the tilted camera setup. A tilted specimen has the same effect. Reasons for tilting can be that the specimen is not clamped straight lengthwise, or the testing machine does not pull straight. Here again we have a numerical example. Let's assume that the specimen is tilted by 1.3 degrees. The specimen is 150 millimeters long. The tilting leads to longitudinal pseudostrain of 1%. We have the same pseudostrain than we had for the tilted camera setup. Let's take a look at the local effect on a specimen now. The specimen can show, for example, dents, bulges, or slight ripples. When clamping the specimen, it might also come to bulges. Bulges do not influence the 3D measurement. In a 2D measurement, the points are projected onto the calibrated plane. This leads to an out-of-plane error. Let's have a look at this effect in a practical application. Here you see the compression phase of a cyclical tensile test. The surface component shows a displacement in Z direction. The material is compressed. As a result, the material bulges backwards. 2D shows very clearly that the material bulges backwards. The longitudinal strain appears smaller in the 2D measurement than in the 3D measurement. In the diagram, the effects can be recognized even more clearly. The upper part of the material is again on the left side, the lower part is on the right. 2D shows a completely different longitudinal strain than 3D. The reason is that the material bulges backwards. Now we'd like to have a look at the last limitation, cosine error caused by tilted specimen. In contrast to the previous models, this model is shown from the bird's eye perspective, so we look at the measuring setup from above. Therefore you see a transverse displacement and not a longitudinal displacement. This means that the specimen is twisted. By using this equation, the pseudostrain can be computed here as well. Imagine that you clamp a specimen that has a width of 20 mm. When you tilt it by 0.7 mm, you create an angle of 2 degrees. A tilting by 2 degrees leads to a pseudostrain. The cosine error especially affects derivative values. In a tensile test, these are Young's modulus, and Poisson's ratio. The displacement in z direction shows that the specimen twists at the bottom. The left part moves further forth, the right part moves further back. This effect can occur when the specimen is not clamped optimally. For example, when there is grain between the wedge clamping jaws, or due to small movements under growing load. Let me show you an example to illustrate this effect: the ratio of longitudinal and transverse strain. In the 3D measurement, we have a fixed ratio of longitudinal and transverse strain for the entire test duration. This is exactly what can be expected for the used material in this strain range. As you can see in the diagram, the 2D measurement significantly deviates from a straight line. In this case, only the transverse strain is affected. The computation of the derivative value would be inaccurate. The gradients of the linear equation differs by 30%. To sum up the limitations, here we have again the slide with the overview of the limitations. The various effects might also overlap. The propagation of uncertainty can be calculated using the following equation. SF represents the standard deviation of the function f. Sx represents the standard deviation of x, and so forth. In this case, we assume independent parameters. An error can be compensated by another, or added up, resulting in multiple errors. For example, in a 2D measurement, the pseudostrain can be increased when the specimen is clamped in a tilted position and at the same time the camera is not positioned straight towards the specimen. You can never be sure if and which pseudo effects occur in a 2D measurement. Let's have a look at the comparison between 2D and 3D. Coordinates are measured dynamically only within one plane if you have a 2D measurement. Points that are out of plane are projected onto this plane, which can result in inaccurate data. Only flat specimens can be measured. The camera must be positioned vertically towards the specimen in order to prevent pseudostrain. For displacement, you need a scaling. 2D measurements require manual scaling. The scaling is not very accurate, as you have to click pixels afterwards in the software. In the 3D measurement, you have a dynamic measurement within a volume. That means you get 3D coordinates over time. 3D measurements are suited for specimens of any shape and any size, regardless of the specimen thickness. Any type of motion can be analyzed, therefore. The measuring system can be set up flexibly. It is also a robust system that is not as prone to errors as 2D. And you can also analyze displacement precisely. Due to the calibration, the images are automatically scaled. Let's have a look at some application examples of 3D measurements. Let me show you a high-speed test as an example. Airbags need to deform within milliseconds. You will now see the opening of the airbag housing. Optical high-speed measurements allow us to analyze in detail what exactly happens during the opening. When opening, the airbag housing does not deform only within one plane. A 2D measurement therefore would not provide valid results. Here you see the displacement of the airbag housing in Z direction during the opening process. This analysis is only possible in a 3D measurement. Let's show you a new example. Here you see a sled crash. We have seen it before how you can evaluate it in 2D. It simulates a crash at a speed of 25 km per hour. Here you can see the translation and rotation of the head. The nodding movement represents the rotation around the y-axis. In addition, there is a rotation around the x and z-axis. The rotation results from the asymmetrical load distribution at the 3-point seatbelt. This rotation is only visible in a 3D measurement. This means that the 3D measurement provides more information than the 2D measurement. With optical 3D measuring systems, you can also analyze the stiffness of a prosthesis in detail to find out how to reduce the relative load on the knee. We have seen this example before for 2D motion analysis. Here we can see now that you have more information about the movement of the leg prosthesis. You can see the displacement in X, Y, and Z direction. In this case, 3D provides also more information than 2D. To sum up what we have here now, a stereo camera system is the best way to optically capture coordinates completely. It provides extensive measuring data. Besides, it is a more robust system. The system can be set up very flexibly. 2D measurements are captured with only one camera are good enough when you can tolerate the limitations. 2D measurements are often used for very small specimens or if you have a high-speed test. That's all for today's webinars. You might ask yourself which system you need for your application. Markus Klein will give you detailed information on this matter.
Thank you, Julia. So going a little bit further with this and away from the technical discussion regarding issues that occurred in 2D testing, it depends really on the application. What is a good solution to be used, 2D or 3D? With the GOM Correlate, there is an option that enables you for free to try out the 2D measurements, but you need to be aware of these issues that might happen. With 3D, of course, all these issues can be overcome due to a stereo camera setup with the ability measuring in 3D space and, of course, with accurate lens distortion corrections. So the GOM Snap 2D program is a part of basically GOM Correlate that you can download from our homepage, or looking on the microsite gom-correlate.com, there is the software available for download as well as a few projects, sample data. There is more information available also in the GOM service area under support.gom.com for GOM Snap and for GOM Correlate. GOM Correlate, in addition, acts also as a free evaluation software for 2D and for 3D projects. So if you did a 3D project already and want to evaluate this or share it with colleagues, feel free to use GOM Correlate too. 3D measuring systems, of course, do have advantages in terms of out-of-plane motion detection. Another issue that needs to be considered for all kind of optical measurement is the lighting. So therefore, a good measurement needs to have a good illumination. Depending on the frame rate, lamps need to be more powerful than for slow speed measurements, for example. But it is important to provide a proper illumination to ensure enough image contrast and to ensure short shutter time for faster motions. So 3D systems basically do have a stereo camera frame on which the cameras are mounted to provide enough mechanical stability and thus provide accurate 3D coordinates throughout the measurement. Training is another question, of course, that we always get. If you are interested in a training session, we can offer you this in our offices, or you can go in contact with our distributors worldwide, which are offering you standardized training sessions for Aramis, respectively GOM Correlate too. There are a few more webinars available, on one hand, to explain the workflow and the functions in GOM Correlate. There are 6 short videos available for that. On the other hand, there are other videos which discusses applications like automotive or aerospace testing. Biomechanics is also available. Feel free to check our YouTube channel under GOM Metrology for this, or go into the GOM service area if you do have an account there already. The next webinar is coming up on May 24, discussing the determination of forming limit curves, so the material deformability for stamping operation. Feel free to register here. We're going to give you an outlook how this works in the new software version 2017, which is coming up in July. We will stay tuned for a few more minutes. If you do have questions, feel free to answer in the Q&A tab. This webinar is recorded and will be uploaded to YouTube in the next days. So if you want to review that or share with colleagues, please feel free to do that. Thank you very much for your attention and see you at the next webinar.